Hello friends. In this video we are going to answer this question. A solid homogeneous cylinder of radius small r without slipping on inside of a stationary large cylinder of the radius capital R. So this is the system they are talking about. Here I have drawn the side view only. Find the equation of motion and what is the period of small oscillation about the stable equilibrium position. So that means, so this is not a circle, this is a cylinder. Okay, I have drawn the side view only, and this is the smaller cylinder within this larger cylinder, right? So now you see, first let us consider the stable position, that is equilibrium position. This is the equilibrium position of the larger cylinder, and here is the suppose smaller cylinder within it. So let me take this is the radius of the larger cylinder, and also let me mark it the smaller radius. This is smaller radius of the smaller smaller cylinder. Okay, so now you see, suppose if you move this one, if you roll this one this way like this in clockwise direction, and it will roll, and suppose it takes this position. Let me consider, suppose it comes to this position. Let me draw another picture. Okay, suppose, just wait, in order to explain this, let me draw another picture. So here is now at this position. So this is the radius capital R, and so now you see, so if you mark this radius smaller using some paint, some kind of paint, or using marker like this, so when it will rotate this way, the radius, this marked radius will also rotate, right? Suppose this is now at this position. Okay, and this line joining the centers comes to this position. Okay, this is O and O this. So now you see, this is now capital R minus smaller this length, because this part is the this is the line joining the two centers of the two cylinder, right? So that is equal to capital R minus small r. Okay, capital R minus small r, this part O this. Okay, so it makes phi angle, right, with capital R, with the vertical. Suppose it makes an angle phi, and whereas this is small radius that I have marked here, this makes angle theta with the horizontal. Suppose angle theta with the vertical, not horizontal. When the line joining the two centers O and O this makes angle phi with the vertical, or you can say the angle made by the radius of the larger cylinder drawn through the point of contact. Suppose this is the point of contact of the two cylinders. Okay, and that radius makes angle phi with the vertical, and the radius, this radius is small radius that I have marked here, this radius, this is small radius. When the radius of the larger cylinder that's drawn through the point of contact makes phi with the initial r, that is with the vertical, then this small radius makes angle theta with the vertical. Let me assume that way. Okay, now you see, just wait, let me clean this figure. Suppose this is a horizontal surface, you have a cylinder like this. So I have drawn the circular end only here. Suppose now you see, so this is the radius is smaller, and if you roll it, suppose through a very small angle, let me take a very small angle. Suppose when you roll it from this position to this position as it moves. Suppose this R rotate through this angle with the vertical theta. Okay, then this arc must be equal to this distance. Okay, so I have just wait, let me draw this one here. Okay, this is the new position of this cylinder, suppose circular end of this cylinder, and this same radius is now at this position after rolling it through this very small distance. Okay, then in that case, when it is moved through a very small distance, this much, then here you see, if you take this arc as this radius now comes to this position, as this goes to this position, right? This is the radius. This radius is now at this position, which makes theta angle with the vertical. Then this distance covered by it must be equal to this length of the arc, right? This length of the arc, that going to be given by small r into theta when theta is in radian. And now you see, as it moves through this small distance from this position to that position, okay, so same distance is traveled by the center as well, right? Same distance is traveled by the center. So when this cylinder is rolled from this position to this position, okay, so the arc, this arc that I have explained now, this arc, and as I have considered here very small displacement from this to that, okay, length of this arc and this distance is equal, and also it is equal to the distance traveled by this center, right? So here this was the initial position, suppose, okay, now instead of this horizontal plane, it is rolling over this surface, right? So this is the distance covered by the center. Okay, from this figure what we have understood, so here you see, from what we have understood, this arc, here you can see this arc, okay, subtended by this small radius, angle subtended by this small radius is theta when it is rolled over this surface through a very small distance, this much. Okay, so then this distance is equal, that must be equal to this arc, right? And that arc is also equal to this distance, okay, this distance covered by the center. These two distances are equal, and those are equal to this arc. Okay, if that is the case, here you say this small arc is equal to r theta, and what will be the distance covered by this center when you rolled through this distance? That will be given by this arc, right? This is O, this is the center O, this, right? This is the center O, this, it is moved from this position to that position, right? So if you want to find the distance covered by the center of the smaller cylinder, so you need to find the length of this arc, right? Length of this arc, because this is not in horizontal plane now, okay, like this. Okay, now this distance distance traveled by this center O, this is the center of this smaller cylinder, okay, that is equal to this arc, and this arc is given by r minus, here you see this distance is r, capital R minus small r, so capital R minus small r into phi, and which must be equal to this distance, and this distance is equal to this arc is small r, right? So whose length is r theta, so that's why we're gonna get this equation, r theta is equal to this, right? So now let's start what to do next. So here you see, I have already written what I have considered here. Okay, so now let's go to the equation that we have got now. This equation. Okay, so here you see this is the equation of constraint. This is the equation. If we differentiate it with respect to time, because here this angle changes with time, right? So here theta dot means d theta by dt, and theta double dot means second order derivative of theta with respect to t, right? So hope you have understood this. Similarly phi as well, if you write phi dot, that means derivative of phi with respect to time t. If you write double dot, then it's gonna give you second order derivative, right? That's it. And m is the mass of the smaller cylinder. Okay, let me take this one as equation number 1. So kinetic energy, there are two kinds of kinetic energy. One is translational and another is rotational. Okay, so now you see we know that d theta here, d theta dot, this theta dot, that's gonna give us angular velocity, right? And relation between the linear velocity and angular velocity is r into omega. So omega is theta dot. So here this r theta dot is nothing but our linear velocity, right? Okay, so similarly the linear velocity of this center from this position to that position is given by this capital R minus small r phi dot, because this length is capital R minus small r, right? So hope you have understood this. Okay, so therefore what we have got here in this case, this translational motion of the center of this cylinder, smaller cylinder, from O to O dash. So if this length is capital R minus small r, then and you see its substance angle phi. Okay, so just I have drawn this one here. It's supposed to be at this position, vertical. Okay, so that means let me show you another figure. Okay, this is the perfect position. Okay, vertical. Okay, so hope you have understood. So as this ruled through this, then its substance angle, this arc, this O dash center subtended by this center, at this center of the larger cylinder, angle subtended by this arc is phi. So therefore, and this length is capital R minus small r, so its angular velocity is omega is equal to phi dot. Okay, and linear velocity will be given by v, capital R minus small r, into phi dot. So phi dot is omega, and we know this relation, v is equal to r omega. So instead of r we have capital R minus small r here in this case. So hope you know these things. Okay, so now you see, that's why kinetic energy is, translational kinetic energy is half mv square. Here v is nothing but half capital R small r phi dot. So mass is small m, that is small m, right? Small m. So v square is nothing but capital R small r into phi dot whole square, right? So that's why we have got this translational kinetic energy. And rotational kinetic energy is given by instead of mass, in case of rotation we used to write moment of inertia and theta dot square, right? Theta dot square. So angular rotational kinetic energy is given by I omega square. Here omega is theta dot, and I is the moment of inertia of the smaller cylinder about its axis. Suppose this is the cylinder, about its axis means about this line. Okay, so hope you have understood. That is given by half mr square. Okay, so that is what we have done here. This I is replaced by this half mr square. So there is already one more half here, so half into half we have got. Okay, and if we simplify this, then we're gonna get this. So here r square dot r square into theta dot square, what does it give? R into theta dot is equal to this one. So when you square this, then you're gonna get square of this, right? Okay, so now this is replaced by this result from equation number 1. So using equation number 1, we have got this expression. So once you put this here, you see what we have got: half m capital R small r whole square phi dot square, and plus this 1 by 4, 1 by 2 into 1 by 2, that's going to be 1 by 4. Then we have m, this r square theta dot square is replaced by capital R small r into phi dot whole square, or you can write simply this way, this square into this square. Then if you take LCM, okay, if you take LCM, then it if you add these two quantity and if you take LCM, then it's going to be 3 by 4 into this. So here I have written using 1. So hope you have understood this. So now let's take this result, this kinetic energy equation, T is equal to this, as equation number 2. Now let's go to the next slide. Here you see potential energy. Now what will be the potential energy? So here we have take this as a reference point. So what will be the height below this point? This one. So here you see this is nothing but here you see this length is capital R minus small r, right? So now consider this triangle. This is capital R minus small r, this is angle phi, right? So what will be the length of this one? Suppose this is O A B. So here cos phi is equal to this is base by hypotenuse AO by OB. Then AO is equal to OB cos phi. So here OB is nothing but R minus capital R minus small r. That's how we have got this one. So we know potential energy mgh. So instead of h, we're gonna write this part, which is as we have taken this one as a reference point, and this height is going below it. So that's why we have put here negative sign, and this is the height in this case. Okay, and mg into h. So here it is mg. G, you know, acceleration due to gravity. So hope you understood these things. So now you say what we're gonna do here. So let me clean it. Here you see 4 phi is equal to 90, cos phi will be 90, then potential will be 0 here. Okay, potential will be 0. At this position, when this small cylinder will reach there, so we have considered this is the 0 potential level actually, right? We have considered this is the position of 0 potential. Okay, that's why when we have taken this height, so we have taken negative. Okay, because it is below the reference line, so that's why we have taken the downward direction as negative direction. Okay, that's it. And use the Lagrangian. We know Lagrangian, this is L, which is T minus B, kinetic energy minus potential energy. So we have got T from this equation number 2. Here you see from this equation number 2. So let's put here T is equal to this one that we have put from equation number 2, and there is minus, and again we have minus here. We're gonna replace this value of V. We're gonna put this value of V here. So minus minus, that's gonna be plus. So here we have got plus mg into capital R minus small r cos phi, right? So now the equation of motion, this is the equation of motion, Lagrange equation of motion. Okay, so now let's obtain del L by del phi dot. Okay, let's define sheet L. Let's define this Lagrangian with respect to phi dot. So here first part is only the function of phi dot, this part is function of phi. So that's why if you differentiate partially this part, that's going to be 0 with respect to phi, with respect to phi dot. And if you differentiate this with respect to phi dot, then this phi dot square gives you 2 phi dot, right? And this 2 and this 4 cancels, that's going to be 3 by 2. So hope you have understood this. So that's why we have got here 3 by 2 into m r minus small r whole square phi dot. That's what we have got. And here you see, now you see what we can do. Again, let us differentiate this with respect to time. If we differentiate it with respect to time, then what we're gonna get? We're gonna get this term. We are trying to obtain this term, right? So if we differentiate it with respect to time, so we know phi dot is nothing but d phi by dt. And if you differentiate it again with respect to t, then you're gonna get this, right? So which is nothing but double derivative, second order derivative, phi double dot. So that's why we have got here phi double dot. So hope you have understood this. And let's obtain this part of this equation of motion. And if you differentiate this L Lagrangian with respect to phi, now this part is function of phi dot. So that's going to be 0 if you differentiate it partially with respect to phi. So let's differentiate this partially with respect to phi. Then this cos phi, that's going to be minus sine phi, So that's why we have got this result. Okay, we have got this result. Now if we put this value here in this equation number 4, this minus, that's going to be plus. Okay, so using these results, so let me clean these things, just wait. So now you see, using this set of results, this one which is equal to this one, right, and this one which is equal to this one, and using these results in equation number 4, we have finally got this result. Okay, this is the equation of motion, right? So hope you have understood this. And let us divide this equation both sides by m into capital R minus small r. Then if you divide it this, then this one gonna be cancelled, mm gonna be cancelled. Okay, so and then this equation is reduced to this form. That is suppose equation number 5. And for very small oscillation, phi is very small, and for very small phi, sin phi is almost equal to phi. And if that is the case, we can replace this sin phi by phi, and then we're gonna get this equation of motion. This is the answer to the first part of the question. This is the required equation of motion. So let me go back to the question. Here you see, this is find the equation of motion. Okay, now what is the period of small oscillations about the stable equilibrium position? So here you see, let me go back to the last slide that we have got. Here you see, so we can write this equation number 6 in this form. Okay, so that means what we have done, we have divided each and every term by this quantity, 3 by 2 into capital R minus small r, and doing so we have got this equation where omega square must be equal to this part, right? Okay, so I have skipped one step, that is what, if you divide this equation by this quantity, so this one will be cancelled, and here we're gonna get g by this part, right? And 0 by anything is 0, so that part is nothing but omega square. Okay, so hope you have understood this. So now from this equation, so now let us take this part, then let me go to the next slide. So here is the omega square, then if you remove this square, then there will be a square root. So that's how we have got this. Okay, so this is the period of small oscillation. We know t is equal to 2 pi by omega, so that's how we have obtained the period of small oscillation, right? So here this is omega, so 1 by omega will be the reciprocal of this one, so we have put the reciprocal of this one here, reciprocal of omega, so to obtain the answer to the second part of the question, that is the period of small oscillation. Thank you for watching. See you in the next video. Bye bye.